So last time we were talking about finding Fourier series and figuring out what those Fourier coefficients were for functions that had periods of 2 pi. So let's just do one more example like we did last time, and then we'll talk about how we change over to doing functions that have periods other than 2 pi, which is just it won't be that bad. So we'll do several examples of those. So let's say we had our function f of x is, it doesn't really matter. Let's say we have something like, let's do another one that's got a couple of pieces to it. Maybe it's 1, or let's say it's pi from 0 to pi. And then from there, we'll slope down. So let's say we do 2 pi minus x for x between pi and 2 pi. And then again, when I write this down, I'm assuming that I'm writing down one period of the function so that it will repeat over and over again. So if we think about what this graph of this function might look like, the first part starts here at pi, goes over flat until we get to pi, and then the way I've drawn it, or defined it, I mean, it should start at pi and then slope down to 0, and then do the same thing over and over again. So it's something that looks like that, roughly. Okay. So hopefully we'll get something that looks like that when we're done. Okay, that's our goal, right? So what we assume that we'll see is something that'll kind of tick along here. By the time it gets to here, though, it'll have to jump, and then it'll tick along here and do the same thing around, right? So I assume we'll see at the end. All right, so remember how we find these different coefficients. What do we have to do first? Yeah, we need to find our A naught, we need to find our A sub n's, and we need to find our B sub n's, right? How do we find our A naught? Okay. Good. So we're going to do the 1 over the pi integral from 0 to 2 pi of the function, right? Okay. When we wrote that 1 over pi piece, it's because that we're trying to make it mirror the other a's, right? Your other a's are the cosine pieces. And if I let n equal 0, then I get the exact same formula for that, right? Instead of cosine for the b's, we use what? The sine. Good. All right. So usually I do this when I'm doing them, I do it in 3 stages. I'll find the integral for my f, find the integral for my f times sine, and my f times cosine. It doesn't really matter the order, just that's what we need to do to find these things, right? I need to find those 3 different integrals. What do the coefficients out in front here represent, by the way? Where did the 1 over pi, in particular, where did the 1 over pi come in for these two? Bless you. Bless you again. Okay, so yeah, there's a specific reason why we had to use pi. That number is actually going to change when we do stuff later on. How do we find that pi? Remember what operation does this represent in our function space? What are we doing with this function and this function represented with respect to the function space? a dot product, right? So remember, we're finding those projections. The projection involved the dot product of the function with our basis function, one of the trig functions. What was in the denominator? Yeah, the dot product of the trig function with itself, right? So remember that this pi on the bottom represented our integral from that pi on the bottom was the integral from 0 to 2 pi of cosine squared of nx dx and the sine squared nx dx, right? That was what the pi came from. We have to divide that out when we're doing our projections. Again, if we change the period, this number is probably going to change. Like I said, we're going to do several examples of that today. But just to remind now that that's where that pi comes from, is that fact that we are doing projections onto the space, and I need that coefficient in there. In linear algebra speak, we're normalizing the basis. We have an orthogonal basis, and we're normalizing it. That's where that piece comes from. In any event, it's important to remember that pi is coming from doing the dot product of that function with itself. Because we're going to come back to that here in a little bit. All right, so we need to do all of these, and then remember when we're done, this a naught, we have to divide it by what? 2. It's always half of that, right? So, pardon me. Basically, when we're getting that a naught over 2, it's because when we do the integral from 0 to 2 pi of 1, that's our other basis vector that we have besides the sines of nx and the cosines of nx, right? Notice that has 2 pi for its integral rather than 1 pi, right? That's why there's an extra 2 on the bottom. All right. So let's kick this over to GeoGebra because we're not going to do any of these by hand. This one's a piecewise defined function. So since it's a piecewise defined function, I think it's easier just to go ahead and type both integrals in at the same time and add them together. Right? I have to split the integral into 2 since we have a piecewise defined function. I'll rewrite it on the board here so that I remember what I wrote down. We had pi between 0 and pi and 2 pi minus x between pi and 2 pi. So when I do the first one here, remember again, we just need to integrate the function over the integral over the interval. The function in this case, the first part of it's just pi. And then I'll add the integral of 2 pi minus x oops. Apparently I didn't hit the enter key. There we go. Try that again. Okay. Oh, I forgot to remember. Shoot. I did this in the algebra window. That's why it's giving me gave me a variable name. Remember, I want to do most of these integrals in the symbolic window because we'll have n's in the next ones. It's okay here, but let me get that up here. Let me change out of the algebra view and back to the computer algebra system view. Sorry about that. You'll want to make sure that you're in the computer algebra system window, the CAS window, because we're going to be doing those integrals with respect to x, and then it's going to have an n in it, so it needs to be able to handle that symbolically. If you leave it in the algebra window, it's going to try to create a slider for the n, which means that you could slide the value of the n's and it'll change the integral for you automatically, but that's not very helpful since we're looking for a formula. All right, let me do that again. So this one I need to integrate pi from 0 to pi, and I need to integrate 2 pi minus x from pi to 2 pi. There we go. That's a little bit better. Say it again?
How'd you go?
So up in the little hamburger menu thing here, it should be under view, and then there should be a tick box for CAS. So turn off the one for algebra and turn on the one for CAS. All right, cool. Why do they keep putting chairs right where I walk? I don't understand who moves a chair in front of the chalkboard. Stay here early in the morning every day. It drives me bonkers.
Somebody had to have timeout.
Yeah, somebody need a timeout. Wear the dunce cap in the front of the room. All right, what do we do when we actually create our series? What are we going to divide this by? Pi and then an extra 2 as well, right? We'll divide this thing by 2 pi when we're done. So when we actually create our series, our constant term will be 3 pi over 4. We'll come back to that here in a second, but just to remind that we need to divide that one by 2 pi. Okay. All right, so then the other ones, you're going to do the exact same thing, except that I'm going to multiply the function times sine of x to get my b's, or sine of nx to get my b's, and cosine of nx to get my a's. Doesn't really matter which one we do first. I'll do the cosines since we already recognize that as being an a. Again, for the first half of the interval, the function is pi. And then for the second half of the interval, the function is 2 pi minus x. Darn it. I forgot my cosine of nx on that one. Sorry about that. Oh, and this GeoGebra is really, really clunky about its parentheses. There we go. So for the second half of the interval, we use 2 pi minus x for our function. So I'm doing 2 pi minus x times cosine of nx, and then we're going from pi to 2 pi. Since I've got inside my integral, in my integrand, I've got 2 variables, an n and an x. I want to make sure I tell it what variable to integrate with respect to. I do believe that by default, if you leave that out, GeoGebra will integrate with respect to x, so I'd rather not take a chance. Okay. Now, if you want to be super clever and not have to retype whatever coefficients that we're getting in these, you can also define this as a function of n and then refer to it later. What I mean by that is, if I go back over here in the front and say call this a of n and define the function as a function of n, then later on when we create, it didn't like a because I already used a before, that's why it changed it to a b. Remember I typed that other expression in the algebra window and it defined it as an a? It kept a in memory, and so it flipped it to a b. That's why it changed it to a b. In any event, if you don't want to have to retype it all, I know that we could analyze it. For example, we did this before, and we'll do this again here in a little bit with a different example. But if I look at this piece right here, I know that this is always going to equal what? No matter what I plug in for n, what's this always going to equal? 1, right? So I don't need to have to, if I were to type this in later, I could just type in a 1 instead. But if I define it as a function, then I can just use it as the coefficient and not have to retype it every single time. Notice that. Does that make sense? We'll actually go to form our series. How does this change for the other coefficients that we need? I need to change the cosines to what? To the sines. Good. So in this case, I'm just going to grab this and copy it. And then, I don't know why it just did that. Hit copy, paste. There we go. And I'll just type in GeoGebra is super clunky with different things like this. Get off. There we go. All right, so I just went in and pasted it and changed the signs. If you're having issues with the copy and paste, which is certainly possible because it likes to try to re-put things in there for you that you didn't want to put in there in the first place, you can just retype it all. It likes to be super clunky. Again, if I want to refer back to this later, I can give it a name. Now that the computer already took up a B for me, GeoGebra already took up the B for me, I'll call it C, since I don't have C defined anywhere. Again, there's a little bit of superfluous information in there because we know that what's sine of n pi and sine of 2 n pi going to be all the time? 0, right? But again, this will just save me hopefully a little bit of typing later on, and then the format's going to be the same every single time when we do this.
Bro.
What happened?
It went away. It doesn't even matter at this point.
Okay.
Somehow I deleted everything I wrote down.
Oh, nice. Yeah, like I said, GeoGebra is a little clunky sometimes. It's nice that it's free and it's nice that it works. It's not so nice when it's clunky. Yeah. I didn't say it wasn't clunky.
The page may have refreshed because anytime you refresh, it saves us nothing. So.
Right.
If your computer just decided you needed to refresh, then
Yeah.
Screw you, I guess.
Pretty much. All right. So now we should be ready to form our series. Okay. So our f of x here. We'll define our f of x. Remember again, if I actually want to see this plot, I need to define it as a function. This was our constant term, but we said we needed to divide it by 2 pi. So the constant term in this case will be 3 pi over 4. Then we'll use our sum command. Notice we've saved our coefficients in there. We've saved our b of n's and our c of n's. So we can use those to type in the expression. So we will do b of n times cosine of nx. Because the b's, I know we used a different letter here, but that was because I told you GeoGebra's clunky. The b's came from doing these integrals with the cosines, so those are the coefficients on the cosines. So we'll do b of n times cosine of nx, and then plus c of n times sine of nx. The variable we're summing up is n. And we always start this at 1. And then we just pick an arbitrary ending point so we can see what the graph looks like. Remember, these are going to be infinite series in general. We're going to make a finite series so that we can actually plot it and use it for something. Right? So you're going to use it what we refer to as a trig polynomial. We're just stopping it somewhere, so it makes a trig polynomial. Doesn't matter. Pick an n value. I'll try 10 to start with, just to see what it looks like. And that doesn't look right. So something's not quite right here. Close, but it's not quite right because it should stop at 0, right? Shouldn't dip below the x-axis. So let's see. Oh, I know what I forgot. What did I forget? We did forget something. The 1 over pi, right? I didn't put the 1 over pi in front of these pieces, correct? We didn't divide by the pi. Go back up here. I can put it all the way out. We can actually factor that all the way out of the sum. So I'll do the 1 over pi. There we go. That's much better. And now you can see that's what we're supposed to be getting there. Wiggles along at pi for a while and then drops down. When we get to 2 pi, jumps up, wiggles along for a while, goes down to the next 4 pi and then jumps up again. Let me Scooch over a little bit so you can see it a little bit better. That one okay? Again, if you change your upper bound on that sum, it should get a little bit better. So let me change it from 10 to 100, just because I can get it to scroll over. Where am I? Oh my heavens. Oh my gosh. Here we go. It'll take it a second to compute it, but there's a little bit better. Again, you would expect it at the endpoints to be bad because it's trying to approximate a jump, a discontinuity, with a continuous function. So you expect that you're going to get noise at these jumps, right? But notice where it's not jumping, even at this corner. It's pretty good, right? Is this okay? Are we okay with the process? It's easy to forget little things as you go along, like I forgot to type in the 1 over pi here. Wait, it didn't like that. Apparently I killed it. What it looks like it says it's dead. All right, any questions on that one? All right. We're going to do several more examples, but I do want to talk about how we can change the period, and then we'll come back to GeoGebra and play with that some more. All right? So, again, the way we created our Fourier coefficients were by, pardon me, were by doing that inner product from 0 to 2 pi, and did the function times the cosine, the function times the sine, or whatever. That way I've got those inner products in that case. So what happens if we change the period? Well, let's if we change the period, notice that we can do basically a substitution idea. So let's say instead of 0 to 2 pi, we did something like 0 to, and just to make the numbers a little bit better, let's say we do 2 times p. So the p is representing the period here. Now, the reason why we used cosine of nx or sine of nx, in particular when n is 1, cosine and sine have period 2 pi, and the rest of them, the period goes down by either 2 or gets cut in half or a third or a fourth and so on down the line when we start multiplying by the 2, 3, 4 and so on. But notice that the biggest period that you have is 2 pi, and all the ones you would multiply it by something to get to 2 pi. So they also repeat every 2 pi. They do it a little bit faster, but they certainly have repetition every 2 pi as well, correct? So the first thing we would want to do is change what our basis would look like to make sure that our basic fundamental one, our sine of something times x and our cosine of something times x has period 2 pi. Or 2p, I'm sorry, not 2 pi. Well, what do we know that we do on the inside of the trig function to make the period go from 2 pi to 2p? What would you do? So, for example, if you wanted the period to be 0 to pi instead of 0 to 2 pi, what would you do? I need to know what coefficient we need in here to change the period. So maybe I say it's sine of b times x. What's the period going to be? It's 2 pi over b, right? Is the period of that thing? Right? Remember doing that? I personally like to think of this. Well, there's a couple of ways to think about it. Personally, I like to think about it as a speed factor. it repeats itself b times as fast now, right? So if you put a 2 in there, it repeats itself twice as fast, so its period changes to pi. So on down the line, okay? Really what you're doing here is a horizontal compression or stretch. And remember, whatever you do on the inside is kind of the opposite of what you think it should do, right? We were multiplying by the b, so it ends up, it divides all the x coefficients by that. Okay. All right, so let's go back to the original question that I asked back up here. I want to change the period from 2 pi to 2p. What does the b need to be? Pi over whatever the period is, right? The p? Yeah, okay. So this needs to be pi here and p here, whatever the p has to be, correct? That's what the coefficient is going to have to be in there to change it to 2p. Sounds a lot more complicated than it's going to be when we actually do this, by the way. Okay. All right. I want to try to do this in general so we think about what the transformation has to be. Okay. All right, so when we do the same thing for our cosine, we'd have pi over whatever the period is times the x. And then remember again, each of these is going to get an n in it, correct, as we go through? Okay. You told me a little while ago that these pi's here came from doing the inner product of the function with itself, right? That's where the 1 over pi part came from. So let's see if we can figure out what those coefficients have to be now that we've done this little adjustment here with the period, okay? So we would need to do the integral from 0 to 2p of, let's just do the cosine squared of n pi over p x dx. We'd need to know what that is, right? Now, we're not actually going to go through and compute it. We're just going to do a u substitution and make our lives a lot simpler. Okay? If I want to do, or something like a u substitution, let's make a substitution here. I want to be able to use the result that we already know. To be able to use this, I want to see, when I'm done, I want to see cosine squared of nu du. That's what I want to see when I'm done, right? Because I know what that integral is, and I want to see 0 to 2 pi is really what I want to see here too, right? Because I know what that answer is. It's pi, right? Okay. So if I want to see n times u on the inside here, what does the u need to equal? The other way around, right? The p over pi x, right? And then your du will be p over pi dx, right? Agree with that? So notice that out in front, you'll have p over pi here. And you really do go, if I put in 0 for x, I do get 0 out for u. If I put in 2 pi for x, or 2p, something's not quite right there. Oh no, that's all right. Because if I put in 2p for x, my u will be, no, if I put in 2p for, what am I doing here? Say it again. Oh, I've got this backwards, don't I? This should be pi over p. My bad. Because if I solve this for x, to figure out what to plug in for x, my x will be p over pi times u. That's what I need to do. I had it backward. Try that again. If I put in 0 for x, I get 0 out for u. If I put in 2p for x, I get 2 pi for u. So that's what I wanted. I still have p over pi out in front. That's correct. Okay. So we just said a second ago that this integral is pi. So what do we get when we do this integral? What do we get? P instead, right? So rather than the coefficients out in front being 1 over pi, our coefficients in front are going to be 1 over p. Remember we said the period was 2p, right? So whatever the period is, you're going to put 1 over half the period out in front. Okay? So that's, instead of having 1 over pi out in front, it'll be 1 over whatever the period is. Okay? So we're going to do the exact same kind of computations that we did before. The only thing that really changes is that instead of having 1 over pi here, you'll have 1 over p. And inside here, we just have to do our, instead of just having a simple nx, or a simple, instead of having a simple nx, we'll have an nx times whatever factor we need to change the period to the new period. Okay. So let's see if we can do a simple, some examples here. Make sure that, since I've messed up what I've been saying for the last 5 minutes, let's see if we can do some examples and really reinforce what's going on. So let's do this function. Let's say we have the function pi minus x, where we have x going between 0 and pi. Again, whenever I'm writing it this way, I'm asking you to find a Fourier series for that particular value, that particular function. I'm asking you, or I'm telling you that that's one period, and then you assume that it repeats. What does this graph look like on one period here? As I go from 0 to pi, what do the y's go from? Pi to 0, right? Graph of that just looks like that. So then I just have another thing like this, and a thing like this, and a thing like that, right? Just keeps diagonal, diagonal, diagonal. If it were going up, it would be called the sawtooth wave. So it's just kind of flipped upside down. That's a pi. It's all right. My bad handwriting. I don't apologize for my bad handwriting. All right. Again, the reason why I'm doing this is so that we can kind of get an idea of what we're trying to see when we're done. The Fourier series should mimic this. The only issue that we should see is where we have those jumps, we should see a line trying to jump off to get from one point to the next when we're done. All right. So your period in this case is pi. If I want to change the period to pi, then what coefficient should go in here to change the period to pi? It better be a 2, right? Remember, whatever this coefficient is here is what you divide the 2 pi by to get the new period. Right? So I'll have a cosine of 2nx and a sine of 2nx and a cosine of 2nx. Right? So when I'm doing my integrals in GeoGebra, I don't want to just use sine nx and cosine nx. I want to do sine 2nx, cosine 2nx when I do it. Okay? All right, so let's do that real quick. And yes, I expect that you'll be doing these integrals in GeoGebra all the time. I don't expect you to do these by hand. Okay. Or if you want to find a different computer algebra system to work with, I'm okay with that too. I don't really care. There are other ones out there. It's just this one typically is the most straightforward one to use. I'm going to reload this just so I can get rid of all the old stuff. All right. So again, I want to change my view. If I reload, I want to make sure I have my computer algebra system up. So I'll change my view back over to the computer algebra system. The first thing we need to do is still need to integrate the function over the interval we're talking about. That's step 1. Okay. The function here is pi minus x, and we're going from 0 to pi. So that's step 1. Now remember that this gets divided by whatever the period is, right? Remember this, I mean, we think about it as that A naught over 2 idea, but I just like to think about it separately. Remember that what we divide this by is integral from 0 to whatever the period is of 1, right? Because that's the function that we're trying to figure out what to divide by. That's the dot product with itself. Well, I said 0 to period, but we could also switch it to any other, shift it. But what number do I end up with if I if I integrate 1 over an interval that has length period? It's just the period, right? So whatever constant we get here, we're just going to divide by whatever the period is. In this case, the period is pi, so we'll divide that by pi when we put it in. Okay. I just personally like to think about it separate because I just need to divide it by the period. Okay. All right, let's do the other ones then. I want to integrate pi minus x times, let me do this. I forgot to name I was going to make a function of n here so I can refer to it. Cosine of 2nx here, right? We said not nx this time, but 2nx. The interval here goes from 0 to pi. Same process, just different constant on the inside of the cosine. Nothing else has changed, right? If you want to be clever and not have to remember what the coefficient is in front of the sum, you can put it in here too, if you'd like, right? What did we say we're going to have to divide by in this case? The period is pi, so we divide by so let's go look over here, right? If we look over here, we said that the answer turns out to be p when we're done, right? So we have to divide by p, or half the period, okay? So if I go back over here, what do we want to divide by? It'd be 1 over pi over 2, right? Or multiply by 2 over pi. And for some reason, it decided it thinks we want to graph it. If you want to turn off a graph of something, you see where this little dot's filled in? No, we don't see it. That's just a toggle on and off there. You don't have to put if you want to put the constants in at the end, that's fine. I just thought if we put it in here, I don't have to retype it later. Okay. What changes for the other coefficients for your b of n? What's the difference between your a's and your b's? It's just sign, right? So we'll have pi minus x sine of 2nx, x 0 to pi, and before I put in the constant, I didn't do it that time. So far, so good? Again, we went ahead and just typed these in to refer to them, but let's look at just real quick, let's look at our AN. 2n pi is always 1, so the numerator there is always 0. So there's not anything there, right? There's no reason to even use the a's. They're always 0. So I'm not even going to bother typing it in here in a sec. Well, actually, that's not true. I'll go ahead and put it in a second so that we can see what the form is. But there's nothing there. Also here, sine of 2n pi is always 0. So this just simplifies to 1 over n. We're done. All right. So let's see if we can get this in here, though, just for what we have. So our f of x, can't see it because it's underneath that. Our f of x will be the sum. I need to divide the pi squared over 2 by pi. So that'll just be pi over 2 plus the sum of our a of n times cosine of 2nx plus our b of n times sine of 2nx. We already took care of the half the period being divided in each of the coefficients, so I didn't need to retype it here because we took care of it in the integrals here and here. Right? Again, I don't really need to put this first part in. I'm only doing that so you can look at the form of it. Okay? We don't really need to put it in there. You always start at 1. This number on the end is just arbitrary so they can get a graph. I like to start with 10 because it doesn't take too long to compute, but if you want to look at something more accurate, add a bigger number. Hit enter. Does this look like we said it should look like? Yeah, we started at pi. I know it jumped up there, but we started at pi, slope down, jumps, slope down, jumps, slope down. Again, if we want to make it a little bit more accurate, if you don't really believe that's what it should be looking like, or it's not looking like you think it should, change it to something like 100. That looks a little bit better, right? These are kind of fun to approximate. At least I think they're kind of fun to approximate these things, especially since I'm doing a lot of work by hand. Okay. Here's a more conceptual question. We have a discontinuity at 0. The function is jumping from 0 to pi. What constant do we have out in front there for our function? Pi over 2, which is halfway in between those. Does it kind of make sense, given what your knowledge is for the trig functions that we have, for the way that they behave? They go up and down, and there's a kind of midline there, right? Kind of makes sense that it would do the average of these two values here, doesn't it? At that particular value, that's making sense to here that coefficient here in the middle should be about half of what is in between those discontinuity points. As a matter of fact, if we would have gone ahead and said define the function to be pi over 2 at 0, this would be a same Fourier series. It wouldn't have changed anything. Anyway, so far so good with that one? All right. We're going to do a few more examples of this, but I want to go back and play with the series types of questions that we had last time. Actually, I need to go back over to GeoGebra again. We said that our A subhens here were 0 all the time, and our B subhens here are always 1 over n, right? Okay. So we could say that our f of x here was pi over 2 plus series from 1 to infinity of 1 over n sine of 2nx, right? Yeah. Okay. So, in particular, let's say we were trying to, pardon me, get a value out of this that, what are we trying to do here? If I put in, let's pi over 2, right? Yeah, it was pi over 2. Oh, I know what I was doing. If we want to put in, say, pi over 4 in for the function. So if I want to do f of pi over 4, okay? Our f of pi over 4 should be, I forgot what number I wanted to plug in. That was my problem. That value. If they're really going to be equal with each other, it should be that value, right? Remember, again, our function was, oops, I don't have it written on the same page. Our function was that, wasn't it? If that series is supposed to represent that function, then we should have those values are equal to each other. So if I plug in pi over 4 into the function, that should be the same as plugging in pi over 4 into the series. What do I get when I plug in pi over 4 into the function? What number do I get out? 3 pi over 4, right? So if I rearrange this, we should get that pi over 4 is the same as this series. I should get the sum from 1 to infinity of 1 over n sine of n pi over 2. Right? Agreed? Okay. But let's analyze this a little bit more. What does sine of n pi over 2 do? When I plug in 1, we get. When we plug in 2, we get. When we plug in 3, we get. -1, plug in 4, we get. 0 goes 1, 0, -1, 0, 1, 0, -1, 0, right? So really, the only terms we get out of this series are the odd terms, and they alternate, right? So another way to rewrite this series is the sum from n equals 1 to infinity. I can do the alternating part by doing -1 to the n plus 1. I need to make sure even the odd terms match. And then do just odd denominators. The only terms we have are odd ones, right? So we get odd denominators. If you were to write this out, that'd be 1 minus a third plus a fifth minus a seventh and so on down the line. So now we have a series representation for pi over 4. Bless you. There's another way. If you remember your power series stuff, your Maclaurin series stuff, you might remember that your inverse tangent function looks like, may have written it slightly differently. Looks like that. It has an interval of convergence of -1 to 1. And notice you get the same result, right? If you put in 1 for an inverse tangent, you get pi over 4 out. The right-hand side is exactly the series we just wrote down. This is just another way to get the same series. This is fun stuff. I find it fun. All right. Anyway, any questions on the process we're doing to find these series as we do a couple more examples? We're also thrilled about that particular result, I see. All right, let's do another one. Let's say your function f of x is x squared from -1 to 1. Here's one where we've shifted it from -1 to 1, but that's not really going to matter as far as figuring out the Fourier series. We're still going to do the same integrals. We still have to do the same period adjustment. All this does is just change what our limits of integration are. Shifting is not going to matter. All right. So again, we need to figure out the integral of the function over the interval, and then the integral of the function times sine, and the integral of the function times cosine. The last piece that we need to make sure we understand is how to figure out what the coefficient we need is on the nx piece, right? Because the period has changed. What's the period here? 2. So to change from a period of 2 pi to a period of 2, what do we need to do? Yeah, I got to put a pi on the inside, right? Remember again, if you've got sine or cosine of bx, your period is that 2 pi over b, and we want it to be 2, correct? So the b has to be the pi piece. Right? Okay. All right, so back over to GeoGebra. Let me reload because this looks like garbage. Change back over to my computer algebra system so I can see what I'm doing here. All right. Again, integrate the function, which is x squared, over the interval. Get 2/3. Could have done that one by hand. That was not too bad. What do we divide that constant by? Well, we divide it by the actual period, right? So it'll be half of that, correct? So we have to divide that by 2 when we're done. That one always gets divided by the whole period, right? The period in this case is 2, so it gets divided by 2. Your constant always gets divided by the period. The other ones get divided by half the period. Okay. What is half the period in this case? 1, so that we don't have to divide by anything in the other ones, right? So let's figure out our A's and our B's. What are we going to integrate to figure out the A's? The A's, again, are going to refer to the cosines. What do we integrate to get the A's? Good. Cosine of pi nx, good. Function times your cosine. The pi, again, is adjusting the period from 2 pi to 2. We don't need to worry about any constant out in front here because we divide by half the period. Half the period in this case is 1. So there's nothing to divide by on here. The interval here is -1 to 1. There's nothing else that changes. You just have to integrate over the interval you're given. Okay? Again, I don't care about that particular graph. Notice this one looks a little bit strange with tangents in it. Right? Okay. So we're going to come back to this in a second to try to see if we can figure out a better way to get these things not to involve tangents in them. In fact, it may not like it very much when we start putting in odd multiples of n in there, or odd n's in there, I mean. How do we find the b's? Switch the sign. Good. So we'll do x squared sine of pi nx. X goes from -1 to 1. Not 0 that time. Literally 0. Not a huge surprise. If we think about it, our interval is symmetric across the origin. Sine of pi nx is odd. X squared is even. Even times odd for functions is odd. Integrate an odd function over an interval symmetric about the origin, you get 0. So that one I didn't even really even need to do. Right? That one's just, that's it. All right. So now again, remember we have to divide to get our function. We need to divide our constant by 2 because we have to divide it by the period. So we get 1/3 rather than 2/3. I have my a of n's. Those will be multiplied by cosine of pi nx. I don't need to put the signs in there because we just said those were 0 all the time. Go from 1 to 10 again, see what we got. There you go. It didn't like it very much. Okay. The reason why I didn't like it very much is because those. Did you get things?
Mm-hmm.
Yours is okay?
Not okay,
Oh.
no.
Oh, not okay? All right. Oh, that's fun. So notice that the issue that it had is the fact that it's trying to do these tangents in here and plug those things in, right? Here's a workaround for this particular problem. Let me go back up to my A's. Cosine of pi and x is even. X squared is also even. Even times even is still even. So if I go up here and change this to 2 times the integral and make this go from 0 to 1, it likes it a little better. And I got rid of those tangents. I don't know why it switched over to tangent. So that one we just used our knowledge of what was going on with the function. But now we got a nice little thing, don't we? At least I think it's a nice little thing. Is yours not doing it again?
No, it just crashed.
It crashed?
It crashed you, bro.
Oh, cool. That's what you're looking to do. It looks like I should turn this blue because it looks like the waves.
Trying to change things. But
Is that what we got? Hopefully everybody else got that one too. So again, if you get an answer that's involving a tangent thing in yours, you may have to play around with some integral identities to get that to work out correctly. So that was why we had to change it, because it didn't like trying to put in odd multiples of pi over 2 into tangent, because you're going to get undefined things. Otherwise, just give you a question mark at the end. You're like, I don't know, I quit. Felt like a student. I don't know, I quit. All right, that's okay? Yeah, you all right with that?
you explain how you got the 1/3 out in front of you.
Remember that for the constant term, we have to divide by the whole period. 2. Yeah, so I divided 2/3 by 1, or by 2. I got 1/3.
Where we- oh, gotcha.
Yeah, yep. That all right? All right, let's do another one. I'm going to write this one on the board so I don't have to keep flipping back and forth. The function is going to be f of x is x from, what do I have listed on here? 0 to 1. And 1 from 1 to 2. What should this look like? Yeah, you should go up and over, right? It should go up and over, and then up and over, and up and over, and keep doing that over and over again. A little bit nicer than that. Right? That's what it should look like when we're done? Okay. All right. Let's reload. Or don't reload. Yeah, that's fine. I didn't want to reload. Where'd my mouse go? There it is. All right. First thing we're going to do is what? Integrate the function, right? This function is in pieces. So let's do it as a sum of 2 integrals. So the first integral will be x from 0 to 1. And the second integral will be 1 from 1 to 2. Right? Get 3 halves. What are we going to divide that one by? 2, because the period's 2 again. Agreed? Okay. To figure out our A's, what are we going to integrate?
X times cosine of n pi x.
Okay. So x times cosine of n pi x, y n pi x. Why? What's the pi in there for?
The 2 period.
Good. The 2 is the period, so we need to adjust the inside of the cosine and the inside of the sign with a pi, right? That'll go from 0 to 1. What else do we need to do?
Integrate cosine of n pi x from 1 to 2.
Good. Oh, and I forgot my x in the previous one. Let me go back over here. X. So again, we're doing function times cosine of n pi x. So I've got the first one goes from 0 to 1. Again, I don't know if I absolutely have to put the x in there, but just to be safe, I want to make sure that the algebra knows I'm integrating with respect to x and not the n, since there's two variables floating around in there. Again, if this is something that you wanted to analyze versus just get the graph of this, we would look at these pieces here and see what's going on. For example, your sine of 2n pi is always, what's sine of 2n pi always equal to? 0. Cosine of n pi does what? 1 and negative 1, right? So if it's 1, we get 0. If it's negative 1, we get a negative 2. So that's going to be half of the terms we actually get that are non-zero, right? That's if you want to actually analyze the series. Right now we're just trying to get a graph, see what it looks like. Okay. What do we change to get the b's? Yeah, let's just change. I don't know why that did that. Go away. All right, so our b's, same exact thing. We'll do x sine of pi in x from 0 to 1 and sine of pi in x from 1 to 2. Do I need to adjust? By the way, I didn't say this earlier, but do we need to adjust with a constant out in front in this one? No, because the period was 2. Remember, we always divide by half the period for these. Well, half the period is 1, so there's not any constant put in front in this case. Unless you really want to put 1 over 1 in there. That seems a little bit redundant. So again, your syntax for the A's and your syntax for the B's are identical, except one is cosine and the other sine. Otherwise, the syntax is exactly the same for both of those functions. Again, this is what GeoGebra doesn't understand what you mean by n. It doesn't know that you're talking about integers. That's why it doesn't simplify it. But if you were doing an analysis here again, the sine of n pi is going to be 0. Cosine squared of n pi is always going to be 1. This is going to just be minus n pi over n squared pi squared, so you get negative 1 over n pi when you're done. Again, that's if you need to analyze what's going on. Okay? So you have to use what the results are to be able to analyze those things. All right, so finally now we're ready to create our function. What's the constant term going to be? 3 over 4, because I have to halve that thing above, right? We had to take the 3 halves and divide it by 2. And then we'll do the sum of a of n cosine of pi in x and our b of n times sine of n or pi in x, n 1 to 10 again. This syntax is always the same, right? Whatever you got for your constant, divide it by the period. That's always the same. Here's the constant. We divided it by 2 because that was the period. This, if we have these stored in here correctly, then this is always the syntax for what you want to do for the sum. And again, when we're done here, we should get, hopefully something looks like this. And if you actually, my big fingers don't hit an extra key in there, we hopefully get something that looks like that. Let me get rid of the other two graphs. Does that look like we said it should? Yeah. I think it's pretty cool to do these. Is okay? All right. Let's do one more. It's a little bit more complicated, maybe. Let's say f of x is 3 from 2 to 5, and it's 2 from 5 to 7. All right, what do we do first? Yeah, I'm going to integrate the function, right? In this case, our function is in two pieces again. We could type it in or we could just analyze it. I'm integrating 3 on an interval from length 3. What's that piece going to equal? I have a height of 3 over a length of 3. It's going to be 9. Height of 2 over a length of 2 is 4. 9 plus 4 is 13. Right? Didn't actually you can type it in if you really, really want to, but if I've got constants, I should be able to figure that one out pretty quickly. All right? Height times length. 3 times 3 is 9. 2 times length. 2 times 2 is 4. 9 plus 4 is 13. That's not going to be our constant. What do we need to divide this by when we create our series? 5, right? A period's 5. We divide by the period. So our A naught, well, I shouldn't write it as A naught, because our A naught gets that extra 2 in it. Anyway, let's write our constant is going to be 13 over 5. Okay. Whatever you get for the integral for the function, you divide it by the period. The period is 5 here. All right, what's next?
Figure out what goes in our sine and cosine.
Good, yeah, got to figure out what goes with our sines and our cosines, right? The period is 5. So we set that 2 pi over b equal to 5. So your b is going to be 2 pi over 5, right? Not too bad, right? Okay. So when we do our integral then, we'll have 2 pi over 5 inside that nx piece, right? The sine of 2 pi over 5 nx and cosine of 2 pi over 5 nx. Right? Okay. What constant's going to go out in front of your integral now? Yeah, 1 over pi over 5, right? Because you have to divide by half the period. So you'll get a 5 over pi out in front. 1 divided by half the period. Right? Okay. All right, so back over here.
Where does the pi come into that? If the period is like, and when it
Wouldn't it just be 1 over 2.5 since the period's 5?
Oh, yeah. Sorry. Yep. The period is, yes, sorry, I lied. Your period's 5. It should be 5 halves. Yep, you're right. That was funny. You're right. I'm sorry. I said that wrong. Let me go back to that. The period is 5. We divide by half the period, which is 5 halves. So you should multiply by 2/5. I don't know why I said pi. My apologies. All right. So 2/5 goes out in front here. Our first function is 3, and then it'll be cosine of 2 pi n x over 5, right? It doesn't matter if it's all over the 5 or whatever piece is over the 5, just as long as part of it's over the 5. What did I say? 2 to 5? And then 2 over 5 integral of 2 cosine of 2 pi n x over 5 from 5 to 7. I was still thinking about the B last time, so I apologize for that. All right, so again, syntax is exactly the same as before. This number is out in front, or 1 over your period. We didn't have those in the previous 2 examples because the period was 2. Half the period was 1, right? So this number out in front is 1 over half the period. Half the period is 5 halves. That's why there's a 2/5 out in front. Function times cosine. I had to split it into 2. That's why we've got the 2 integrals. That part okay? Why we have it 2 integrals here? I'm going to turn off the graph on that because I don't care. Notice here, as far as an analysis goes, I could still get rid of this 2n pi here, right? Because that's going to be 0. But these other pieces aren't really going to be very helpful to analyze because n's some sort of an integer. I don't really know what's going on as far as trying to do it by hand, right? So I'm not going to bother trying to simplify that. And I don't know why this keeps wanting to do that. What's different about the B? Yeah, sines instead of cosines. Syntax is exactly the same, but it's sines instead of cosines. Except I just said it was sines instead of cosines, so what am I typing? There we go. Thank you. You'll also notice I'm sitting here hitting the delete key and it's going backward. There we go. Better. More better. Again, we could simplify that first term if we really, really wanted to, but the other two we're not really going to be able to simplify, which again is why it's a little bit easier here to just refer to them by their functions of n later on. That part okay? Okay. Again, we said the constant part is 13 over 5. Is it being weird again?
No.
Oh.
When you set the terms to 1 to 100.
Yeah.
It's very big.
Oh, yeah.
20 digits.
Okay. I'll do 100. Why not? All right. So again, syntax is the same here. Constant goes in front. Your a's get multiplied by your cosines. Again, it's 2 pi over 5 nx, and it's 2 pi over 5 nx inside the sign as well, right? But the syntax is exactly the same. The only thing that changes is what those period things are. Notice that we shifted the interval here, and that also didn't matter, right? It'll take it a second to do this. There we go. What's wrong?
It didn't display the numbers for me.
Oh, it got sad. But it is having a hard time with computations because it's lagging on the zooming in. But again, notice it's 3 for a while, then 2 for a while, 3 for a while, 2 for a while, which is pretty cool. And again, like I said, we're doing this with trig functions. Notice again, near the endpoint, it has issues, right? Which it should. You wouldn't expect this to be good near the endpoints because the endpoints are trying to create a jump. All right. Guess what your homework is going to involve? Fourier series. What? There's 4E series and there's Fourier series.
And 4S.
And 4S series. There we go. There you go. There you go. Try to follow it backward. There we go. We will have an exam a week from Tuesday. We got one more thing that I want to talk about, which is Monte Carlo simulation. So you'll have a problem where you'll need to check the cubic spline conditions. Not create a cubic spline. I will give you a spline or something that's purported to be a spline, and you'll check whether or not it is a spline for those conditions. There will be least squares problem. I will expect you to use Excel. Okay. I know, crazy. There will be a Fourier series, Fourier series. I'll expect you to use GeoGebra, and then the last thing I'll do will also be with Excel. So, all right, just to let you know what's happening. Have a good one. We'll see you on Tuesday. A week from Tuesday. Yeah. Oops, that's not what I want to do.